All right, so let's talk about how we can measure heat of reaction. And we're going to specifically talk about heat capacity and specific heat, which are just about the same thing. The heat capacity, which is given the symbol C, capital C, lots of symbols, and of course calorie was a capital C too, but heat capacity, but that was the unit. This is the measurement. Heat capacity of a sample is the quantity of heat required to raise the temperature of the sample by 1 degree Celsius or Kelvin. The Celsius scale and the Kelvin scale are the same scale. 1 degree is the same in each case. So we can define the heat capacity as the amount of heat per change in temperature. If we rearrange that, we can solve for Q. Q is heat. Heat is heat capacity times delta T. Just to remind you, delta T is just the change in temperature, which would be the final temperature minus the initial temperature. So heat capacity, we call this an extensive property. That means that the more substance you have, the larger the heat capacity is. So that kind of makes sense. The more you have to, the more heat you have to put to raise the temperature 1 degree, the more heat capacity is. This is not probably the best unit to use. Okay, so let's first do an example. So suppose we have a piece of iron that requires 6.7 joules of heat to raise its temperature by 1 degree. So in other words, it has a heat capacity of 6.7 joules. How much heat do we need to raise the temperature of the piece of iron from 25 to 35 degrees? All right, so here's the formula. Q equals heat capacity times delta T. The heat capacity is given to us, and then our delta T is final minus initial, so 10 degrees Celsius, so 67 joules. Just notice that in this case, the delta T is positive. It's going up, so that's why our heat is positive. It requires 67 degrees to raise the temperature. If we wanted to find the heat that was released when the temperature fell from 35 down to 25, these two numbers would be reversed, because final would be 25 and initial would be 35, so it'd be reversed. So in that case, it would be a change in temperature of -10, which would mean the heat would be negative, which would be exothermic, meaning it's being given off. So it's the same amount of heat either way. So if you get a negative term, it generally is meaning it's given off. If it's positive, it's being absorbed. So actually a better unit of measure for measuring heat is called the specific heat capacity. Sometimes the textbooks use the symbol S for specific heat capacity. Your book uses the lowercase c for specific heat capacity, or sometimes it's just called specific heat. So what's different is that this is the heat required to raise the temperature of 1 gram of a substance by 1 degree. So it even gets a little bit more specific. So not only do you have to multiply by the change in temperature, but also the weight of the substance. So that's sort of taken into effect the fact that it is an extensive property. So if you want to find the heat required, now you have to multiply specific heat by the mass and the temperature change. So heat is equal to Cm delta T, where C is the specific heat capacity. So a lot of times it's called just specific heat. So again, remember, if a substance gains heat, that means Tf is greater than Ti, the final minus initial, is positive, delta T is positive, so Q is positive. If a substance loses energy, that means the final temperature is lower than the initial temperature, so delta T will be negative, and therefore Q is negative. Okay, so let's look at an example. Calculate the heat absorbed when the temperature of 15 grams of water is raised from 20 degrees Celsius to 50 degrees Celsius. The specific heat of water is 4.184 joules per gram degree Celsius. So again, you see that the unit even, our specific heat, shows you what you need to multiply by. Since what you're trying to find is joules, in order to get joules, you'll have to multiply by the number of grams and multiply by the change in temperature. So Q equals Cm delta T. So the specific heat of water, 4.184 joules per gram degree Celsius. If we multiply by the mass of the water, which is 15 grams, and then we multiply by the delta T, which in this case is 30 degrees Celsius, then we'll get the Q is equal to 1.88 times 10 to the third joules, or 1.88 kilojoules. Either answer is fine. Again, Q is positive because we're putting energy in to raise the temperature, so delta T is positive, so this is heat absorbed. Let's look at another example. Large beds of rocks are used in some solar heated homes to store the heat. So the sun heats up the rocks store the heat. So assume that the specific heat of the rocks is 0.82 joules per gram degree Celsius. Again, let's look at this question. What change in temperature would 50 kilograms of rocks undergo if they emitted 450 kilojoules of heat? So this time, keyword is emitted. So that means that the amount of heat is given off, so it's negative. This time, and this time we know the heat, right? We know the heat, and we know the mass, and we're looking for the change in temperature. So again, Q equals Cm delta T. This time we're looking for delta T. So if we rearrange this equation, and first we have to, let's convert, because C is given in joules and our heat is given in kilojoules, we have to convert one to the other. It doesn't matter which one. It's probably easier to convert our 450 kilojoules to joules. So 450 kilojoules is 450,000 joules. Let's also convert kilograms to grams, because again, our unit for the specific heat is in grams, so we have to convert our mass to grams. So if we solve for delta T equals Q over Cm. Because it's emitted, I made the heat negative 450,000 joules being given off, divided by the specific heat, divided by the grams. Notice that my grams will cancel and my joules will cancel. And I actually have 1 over degrees Celsius. So if you invert and multiply, your final answer is Celsius. And and because it's negative, that means that the temperature has dropped 11 degrees because it's being given off. And just, just keep in mind, negatives and positives, that's all it means is the amount of energy is the same. It's just whether it's given off or absorbed. Here are some common specific heats, specific heats of common substances. In lab, we'll be doing one with specific heat of water. I think we'll also be doing, I can't remember. Anyway, I just want to point this out to you. If you were given this on a test, I would give you these values unless it was something you had to find, which means everything else would be given to you. But you would be given these. Just point out that possibly the homework might not give them to you, and they might assume that you would look them up. So they're here if you need them. So again, specific heat of water is 4.184 joules per gram degree Celsius. Just take a minute to think about that. That's actually a pretty big number. The specific heat of water is almost 5 times as great as that of aluminum. So it takes a whole lot more energy to heat up 1 gram of water 1 degree than it does to raise the temperature of 1 gram of aluminum 1 degree, a whole lot more. So 5 times more heat is required to heat up a gram of water. And I guess I just want you to think about that because it's water's specific heat that actually affects Earth's climate. Since it takes so much heat to raise the temperature 1 degree or cool it 1 degree, It's what keeps the oceans relatively resistant to changes in temperature. And also, in terms of our body, since you know a lot of your body's made up of water, it's also important in keeping a constant temperature in your body. So specific heat of water is pretty high relative to other things. So calorimetry is the process that we use, or the setup that we use to measure heats of reaction. So what is a calorimeter? It's a device that's used to measure the heat absorbed or evolved during a physical or chemical change. We're probably going to use in lab, many processes are measured in solution, and so a lot of times that's the easiest way to measure things. In fact, we'll be doing that with water in the lab, measuring changes in temperature in solutions. And just to keep in mind again, an exothermic reaction, what does that mean? Heat is lost by the reaction, so it's absorbed by the solution, and then the solution temperature rises. So if you're measuring, we'll do this in lab, putting something in water, measuring the temperature change. If the temperature change goes up, that means that process is exothermic, that heat is being released. It's being absorbed by the water, which is where the temperature is going up. So an endothermic reaction, then, heat is gained by the reaction. It's taken from the solution around it, and so the solution temperature will decrease. So if we have this calorimeter and the temperature drops, that means it's an endothermic reaction. So here's just a picture of it. So if we look at A over here, A is an exothermic process. So here's the process, and here's the solution, which is kind of like the surroundings. And so the system gives off the heat. The water or solution right here is gaining all the heat, so it's getting warmer, the temperature goes up. So that is an exothermic process. The heat is negative, and the heat is transferred from the system to the surroundings, which is what we're actually measuring, the temperature of the surroundings. So obviously B is the opposite. If the system that we're studying is endothermic, that means heat will go into it. The heat's taken from the solution or the water that's surrounding it. And so once that heat's transferred, the temperature will drop. And again, that's endothermic. Heat is positive, meaning that the thermal energy is transferred from the solution to the surroundings, from the surroundings to the system. What we'll be using in lab is called a coffee cup calorimeter, and so it's exactly what I was talking about. So we're going to have the coffee cup, which is insulated, so we don't want heat to transfer between the outside of the calorimeter. We just want all the heat to stay inside the calorimeter. So it's well insulated. This one's actually got a double cup, but we'll probably just use a single cup. So so it's insulated so that all the heat exchange only takes place inside the cup. Commercial calorimeters are used in industry, and they're generally a much better design and much more insulated, but this will work for us. So anyway, here's what we'll do is, and we may not even have a cover, but we'll have water in there, and then, or the mixture of some kind, and we'll put the materials in there. The reaction will take place. We'll measure the change in temperature. This is a stirrer. We actually will have a thermometer that can double as a stirrer because it's not glass, and so we can stir it up, measure the temperature change, and then we can tell what's happening inside the cup. So a couple of different things. So here, let's well, we want to keep in mind, so like I said, if it's exothermic, the heat is coming from the system into the surroundings and the temperature goes up. And so it could be a reaction or it could just be a physical change. In this case, we've got like a hot piece of metal that's going into the system, into the surroundings. It's transferring its heat till the two temperatures are the same. So we measure the increase in temperature that happens when that transfer occurs. And so it's that change in temperature that will tell us either if we know the specific heat, we can measure overall heat, or vice versa. We can find the specific heat if we know the overall heat. So the point is here, since all of this is done in a calorimeter, that heat exchange is only between, in this case, the metal and the water. So if we put a hot piece of metal into a cup of water, the temperature of the water will increase, the temperature of the metal will decrease. The heat is exchanged only between those two things. We measure the temperature change. So the key is that there's no net change in heat. So all the heat from the metal will be going into the water, and the overall heat will be zero. There'll be no change. So in other words, the heat of the metal will equal the negative heat of the water. So this is a really important point to keep in mind when we use a calorimeter. Otherwise, it's kind of not very useful. So when we measure the heat of the water, and in this case, if the temperature is going up, that means the heat is being given off by the metal, and so they're equal but opposite in sign. Okay, so let's look at an example. Let's say we take a 360-gram piece of rebar, which is just a steel rod, and we drop it into 425 grams of water. The water initially is at 24 degrees Celsius. The temperature of the the water, once the rebar is in there, and the temperature rises, and eventually it gets to 42.7 degrees Celsius. So the question is, what was the initial temperature of the piece of rebar to make this happen? Now we need to have we need to know the specific heat. So if we have the specific heat of the rebar, which is, we're just assuming is the same as iron, it's given to us. And then we're also going to remember that the specific heat of water is 4.184 joules per gram degrees Celsius. So we need the specific heat. And then again, keep in mind that the heat that was lost by the rebar is equal to the heat that was absorbed by the water. And the only difference is that the sign of the heat are opposite each other. So what do we know so far? Well, we know the mass of the rebar, we know the mass of the water, we know the delta T. Delta T will equal 42.7 degrees minus 24. So that is 18.7 degrees Celsius is delta T. We know the specific heat of water, we know the mass of water, so we can find the heat of water. Once we know the heat of water, we know what the heat of the rebar is. It's just the opposite sign. We know the mass of the rebar, and so we can find the delta T for the rebar. So let's do that step by step. All right, so the heat gained by the water is Q equals Cm delta T. So the C is the specific heat of water times the mass of the water times the delta T of the water, 18.7. So if you multiply that out, we get 3.33 times 10 to the 4 joules. It's positive because heat is being absorbed because the temperature is going up. So now the key point is that the heat lost by the rebar is equal to the opposite of the heat absorbed by the water. So the heat absorbed by the heat of the rebar is negative 3.33 times 10 to the 4th joules. So now we can use the same equation Q rebar, but now we need the C of the rebar and the mass of the rebar, and we can solve for delta T. So delta T equals Q over Cm, negative 3.33 times 10 to the 4th joules, divided by 0.449, divided by 360, and we get that the delta T is negative 205.7 degrees. Obviously, the temperature has gone down because it's lost heat. Now, the question said, what is the initial temperature? So we don't want delta T, we want to know what was the temperature before we put it in the water. Well, keep in mind that the final temperature is the same, because that's when the water rose up to 42.7 and the rebar came down to 42.7. That's when they came in equilibrium. So we know that the delta T is temperature final minus temperature initial. If we rearrange it, we know the delta T and we know the final temperature. So Ti equals Tf minus delta T. Think about that. I added Ti to both sides because it's negative, so you want to make sure. So Ti plus delta T equals Tf, or Ti equals Tf minus delta T. So 42.7 minus a negative 205 means that the original temperature was 248.4. So I hope you followed that. It's kind of interesting little problem, but that's similar to what we'll be doing with heats of reaction and calorimeters. Just keeping in mind that the heat lost by the system that we're talking about is gained by the water, so the signs are opposite. Or could be the reverse. The water gained by the system could be lost by the water, but still the signs are opposite each other. Okay, so in that last example, we were just taking a piece of metal and cooling it down. But actually, if you have a chemical reaction that happens inside a calorimeter, the same principles apply. So in general, if you have a reaction that's taking place in a calorimeter, the reaction of the heat absorbed by the reaction is taken from the heat of the water. So again, the heat of the calorimeter will be the negative of the heat of reaction. Whether it's exothermic or endothermic, they will be the energies will be opposite in sign. Whatever we find, if the temperature drops, that's an endothermic reaction. It means the heat of the water is going down, which means the heat of the reaction is going up. So again, the Q of the calorimeter equals the negative Q of the reaction, which is kind of what we just saw. It's just being a little more specific about a reaction versus just a temperature change. So let's look at one more example. If I dissolve 23.6 grams of calcium chloride and I dissolve it in 300 grams of water in a calorimeter, I found that the temperature rose from 25 degrees Celsius to 38.7 degrees Celsius. So what's happening? The temperature of the water is rising. That's the calorimeter. That means that the process of the calcium chloride reacting with the water, or dissolving, in this case it's just dissolving in the water, the process of dissolving calcium chloride gives off heat, energy. It's absorbed by the water, and so the temperature rises. So if we know the specific heat capacity of water, which is 4.184 joules per gram degree Celsius, what is the change in heat per mole of dissolving calcium chloride? All right, so again, we know the heat we can find the heat of the water because we know the mass of the water, and we know the temperature change of the water, and we know the specific heat of the water. So let's calculate the heat absorbed by the water, or the calorimeter. The Q of the calorimeter is Cm delta T. Here's the heat capacity of the water times the mass of the water times the change in temperature of the water, which is 1.72 times 10 to the 4th joules, or 17.2 kilojoules. We know then that the heat of the dissolving of the calcium chloride is equal to negative 17.2 kilojoules. Now, that is the heat given off for the dissolving of, I can't remember the amount, the grams of calcium chloride, but the question said, what is the heat of the reaction per mole? Heat per mole. So what we're going to have to do is take the heat for all of it and divide by the number of moles of calcium chloride that was dissolved. So calcium chloride has a molecular mass of 111.1. So the 23.6 grams of calcium chloride is the same as 0.212 moles. So that heat that was released was for 0.212 moles. So if we divide the heat of the reaction divided by the number of moles, we end up getting the heat per mole, which is something that we kind of need to do to be able to compare between reactions. So, you know, if someone else came along and put a different amount of calcium chloride in, they should get the same value per mole. They wouldn't get the same value because obviously it's a extensive property. So if you put more calcium chloride in, you would expect more heat given out. But once we divide by the moles, what we're doing is we're giving it a relative number. So no matter who did this experiment, no matter how much calcium chloride we use, we can always figure it on a mole per mole basis. And we'll be doing that in lab, one of the labs that we do. We have to be able to compare to other reactions, we need a per mole basis.